Good morning, everyone. Uh, this is Circular Dynamics lecture number 4. Up till now, what we have discussed is that we have seen the basic terms in circular motion, angular position, angular displacement, average angular velocity, instantaneous angular velocity, uniform circular motion, instantaneous angular acceleration, average angular acceleration. We have also seen that acceleration, which is the rate of change of velocity, can be thought of as consisting of two daughters. If acceleration is the mother, it has two daughters. One is centripetal acceleration. Centripetal acceleration is required to change the direction of body, the direction of motion, and it is equal to omega cross v, or omega square into r, or v square by r. It is always directed towards the center. It is also known as radial or normal acceleration or perpendicular acceleration. Then we have tangential acceleration, whose only job is to change the magnitude of velocity or speed. You can also call it rate of change of speed. We have solved some problems on that. So what are we going to do now? I understand that this chapter is about circular motion, but let me give you a brief insight into any particular motion. As I told you, if a particle, if a body is moving along any curve, we can always consider that curve to be a part of a circular motion, and every curve is actually a part of an arc. Now, let us take an example to make this point very clear and we understand how things work. Let us take an example of a body moving on a curved path like this. So, zigzag curved path, any type. Let us suppose that the body is here. Let us suppose that the body is here and this body is moving with a velocity v. Let me call this as v tangential because, as I told you, uh, howsoever the body is moving, you can always think it of as moving along a curve, and this velocity is always tangential to that arc of the circle or that curve. So let me call this velocity as vt. Now, now listen to me very carefully. Listen to me very carefully. Now, this body can have some acceleration. So let us say that this acceleration is like this. The acceleration of the body is like this. Since it is a vector, I'll just mark it with a vector sign. The acceleration of the body is like this. This is the total acceleration of the body. This acceleration a vector is d by dt of vt vector. We all understand this? Can I have some raise hand? Yes, sir. So far, so good. Remember, the topic is circular motion, but we are trying to understand the motion of a general body with the knowledge that we have acquired. Only two people have raised hands. That is not good enough. Let me see whether everyone is there in the class or not. Veronica, Sai, Tarun, Tanu, Shriya, Siri, Satvika, Sana, Sai, Sainath, Khushi, Shashank, Jayashankar, Janu, Deepak, Kartik. Is everyone there? Am I audible and visible to all of you? I hope everyone has woken up, had some nice breakfast, and we are ready to go. Okay, now this acceleration. Now this acceleration A, marking by blue, this acceleration A can be thought of as consisting of two types of acceleration, mother and daughter. What are those two accelerations? The first one is tangential acceleration, the other one is centripetal or radial acceleration. Now, how I'm going to find it out? So what I'm going to do here is I'm going to find out the daughters, and daughter I am going to write by the pink color. So one acceleration, since this is acceleration A, this acceleration A can be resolved into two components. One will be along the AT vector, and that component will be known as tangential acceleration, AT. I've resolved it. And then one component will be perpendicular to this velocity, and that component will be known as the centripetal acceleration. Do we all understand this? Can I have some raised hand that we understand this? This acceleration has been resolved into the two components. One is AT, one is AC. Now, can anyone tell me what is the function of this AT? What is this AT going to do? What is this AT? I've resolved this acceleration A vector into two components, AT vector and AC vector. What is this AT vector going to do? Anyone would like to give any answer? No one has any answer for this? It will change, Surendra, the magnitude of velocity. It is definitely changing, going to change the magnitude of velocity, or simply I can call it as speed. In this particular case, whether it will increase the speed or whether it will decrease the speed. Yes, Karthik, it will change the magnitude of velocity. In this case, whether it will increase the velocity, increase the speed, or will it decrease the speed? Anyone? AT, look at AT, look at the direction of AT, look at the direction of VT. What will AT do? Will it increase velocity, increase speed, or will it decrease velocity, decrease speed? Anyone with an answer? Increase speed or decrease speed here? I'm waiting for answers. AT, tangential acceleration here. What it is going to do? Increase speed or decrease speed? And yes, Abhiram, AT and VT, this is VT, this is AT, they are in the same direction. So it is going to increase the value of tangential velocity or tangential speed. Yes, everyone in the class. Okay, I think students are sitting in the class as well. I have no idea about them. I can't see you guys. I don't know, your camera is not on, so I can't see you. I hope everyone is able to understand this. That is why I think the number of participants in the class, online class, are less. I think most of them are sitting in the offline class. I had no idea. I can't see you. No, your cameras are probably off. Anyways, so this AT is going to increase the tangential speed. What about this AC? What is this AC going to do? What is this AC going to do? Anyone? If one component AT will change the velocity, the magnitude of velocity, the other component AC will always be changing the direction of velocity. And this component is always perpendicular to your velocity. That is one thing that you must remember now. Now comes the important point. Now this AC vector will always point, it is known as centripetal acceleration. This vector is known as centripetal acceleration. This vector will always be pointing towards a center. Oh. Now, the important point here is to understand that even though this particle is moving on a zigzag path, any direction, any path, at any point in time, and mark my words, listen to me very carefully, at any given point in time, it is moving on a circle. And right now, at this moment, this is the circular path that it is following. See this circle. This is the green is the circular path it is following. I hope all of you understand this. This circle has a center. This O is the center of this circle right now. Remember, this circular path ka center will keep on changing because it is moving on a zigzag path. It is just not moving on a perfect circular path. It is moving on a zigzag path. So the center of this circle is going to change because the circles are going to change. This center right now is known as the center of curvature. Do we understand this? curvature, curve, curvature, center, curvature. Do we understand this? Can I have some raise hand that we understand this? This center of this arc, which right now this body is following, is a part of a circle. The center of that circle is known as the center of curvature. Again, this circle has a radius. Right now, I am showing it by this capital R. This circle has a radius. What will be the name? What will I call this radius? Common sense. Physics is completely common sense. Either the names are based on common sense or they are based on the scientists that have found them out. Newton's law. Or else it is based on common sense. So what will I call this radius? If you can tell me, you will always remember it. What will I call this radius? Yes, the class is attentive. This radius will be known as radius of curvature. Radius of curvature. Well done, everyone. Now, it is moving on a zigzag path. So the center of curvature will keep on changing because it's a zigzag path, and this radius of curvature will also keep on changing. It is as simple as that. If it is moving on a circular path, perfectly circular path, then the circle is not moving. The center of the curvature remains same, and the radius of the curvature also remains same. That simple as that. Imagine a sphere, imagine a football. Center of that football, understand that that ball is not moving. Center of that ball. The radius of curvature, you take any point on the sphere, the radius of the curvature is always same. Sphere. Think about three-dimensional stuff. Radius of that curvature is always same, is R. If that ball is not moving, the center is also same. Now, if the ball starts to move, the center keeps on changing, but the radius still remains same. So what I want to tell you here that even though we are specifically studying circular dynamics, and in this circular dynamics, we might not encounter a question where the particle is moving on a zigzag path. But even if it is moving on a zigzag path, the concept remains same. It is exactly same as what we have understood so far. So if I ask you now, if I dare to ask you now, what will be the value of this AC? Can you tell me? What will be the value of this AC? What will be the value of this AC? In this case, right now, at this point in time, where everything is given to you very nicely, what will be the value of this AC? Centripetal acceleration right now, at this point in time. Anyone with an answer? Anyone in the online class? Anyone in the offline class? Students are always present in the offline class. Anyone can tell me what will be the value of this AC? Remember, nothing has changed. What has changed is our perception. What will be the value of this AC? Remember, this is moving on a circular path, so this will always be moving on a circular path. It will be moving with an angular velocity omega. So you can also call this omega. If I call it that way, I can write vectorly this centripetal acceleration as omega cross Vt. Omega cross Vt, as simple as that. If I just want to write it in the scalar form, only the magnitude, I can write the magnitude as omega multiplied by Vt, or it will be equal to omega square multiplied by capital R. This R and this R are definitely same, or I can call it as scalarly V square T by R. Do we understand this? Can I have some raised hand that we understand this? Okay, everything is remain same, even if it is a general motion which is not on a circle, which does not look like a circular motion. It is a zigzag motion, but again, any zigzag motion is circular motion at different points. The radius of curvatures may be different, the center of curvatures may be different, but it is still circular motion. I am not getting enough raised hands, so I must now call upon everyone to wake up, starting from Veronica, Vasant, Tarun, Tanu, Shreya. Is there any doubt? You can always ask. Satvika, Sana, Sai, Rahul, Sai, Khushi, Shashank, Vahini. I hope I am audible to everyone. Janu, Deepak, Charita, Kartik. Are we all there in the class? Do you all understand this? What we have discussed till now? Why is everyone sleeping? I feel that everyone is sleeping in the class. I hope I'm audible to everyone. We understand this. So this centripetal acceleration is same as the acceleration that we had done. Now is the time that I ask you again, what will be the value of this AT? Looking at the diagram, can you now tell me the value of this AT? Looking at the diagram, can you now tell me the value of AT? Everything is given to you right now. We are doing circular motion, but now we have expanded our horizon and seen the most general case of motion, and we are now able to relate it with circular motion. Can you now tell me what will be the value of this AT? What will be the value of this AT? Tangential acceleration. And this tangential acceleration will be simply equal to d by dt of vt, speed, or I can write it as d by dt of magnitude of vt. Do we understand this? Can I have some raised hand that we understand this, sir? D by dt of magnitude. Okay, I may have written it in a confusing manner, so I'll just correct myself and I will write it like this: d by dt of magnitude of vt. Is everything clear? If anything is confusing, please come up to me. I will give you a minute to note everything down. I'll be back in a minute. Anytime, any doubt, you can put it on the chat. The chat is always open. 1 minute to note everything down. I hope everyone has written this. Okay, let us move ahead. Now remember, the heading of this class or this topic is circular dynamics. If I go back in the past, physics gives us a chance to go back in the past, especially this class. When we talked about the term dynamics, what we meant was we must study the cause of motion. What is causing this motion? We studied dynamics before as well. And basically what we are going to study in dynamics, whether it is circular dynamics or linear dynamics or rotational dynamics, whatever, is the cause of motion. What is causing this motion? So basically what we are going to study is the concept of force. Force, dynamics means basically force. We are going to study force. What is causing this motion? Now, Here in this diagram, I think this diagram has become too congested. So what I'll do is I'll just move on to another one, a blank sheet. So now let us try to revise what we know about force. Right. We have this acceleration A, number one. We have this acceleration A, which is nothing but the rate of change of velocity. Let me write it as dvt by dt, because now we are trying to study circular motion. So instead of calling velocity as velocity, we are just calling it as tangential velocity, because we know that everything is a part of a circle and blah, 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 blah. Now this acceleration, anybody has an acceleration, that means a force is acting on it. Then we have Newton's second law of motion, which tells us that the force acting on this particle, or the net force acting on this particle, should be equal to mass multiplied by acceleration. Yes or no? There might be different forces acting on the particle. For example, if I draw a diagram to make you understand this simple concept, revision. This is the body of mass m. If I draw its free body diagram, what will I see? I will see that the weight mg is downward, the normal reaction n is upwards. It's not going to move jhag, 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 jhag. So this normal reaction will be equal to mg. There is no net force. No. But now if I say that there is a force F acting on this particle, and there is a frictional force F, this frictional force F will be equal to mu n. Let us forget that. There is a force F acting on this particle, and there is a frictional force F in the backward direction. But this particle is accelerating, and the acceleration of this particle is A. And the acceleration of this particle is A. And if I ask you to write the equation of this particle, write the dynamics equation of this particle, can anyone help me? How will I write the equation? Division of the previous class, chapter on force, Newton's laws of motion. Can you tell me what will the equation of this particle look like? How does the equation look like? The first equation will look like this. From the yellow thing, what will the first equation from the yellow thing look like? Anyone? No one? What will the yellow equation look like? Yes, the yellow equation will look like this. N is equal to mg, because it is not moving in the upward direction. So these two forces must be equating. So this is the first equation. There is no net force, so N is equal to mg. Now if I look at the green equation, in the green equation I have F in the forward direction and small f friction in the reverse direction, and it is accelerating forward. Now if I write the equation for this green one, how does the equation for this green one look like? It simply look like F minus F is equal to mass into acceleration. Do we all understand this? Can I have some reason that we understand this, sir? Only two people seem to have understood this. That is not good enough. Most of them are sleeping. I don't know why everyone sleeps in the class. If you want to sleep in the class, it's not comfortable at all. You're sitting on a table and sleeping, on a chair and sleeping. It's not good. If you got to sleep on a bed, and then keep on sleeping. So nothing is going to happen with you. Veronica, Vasant, Tarun, Tanu, Shreya, Siddhi, Satvika, Get Up, Sana, Sai, Sainath, Khushi, Shashank, Jayashankar, Deepak, Charita, Karthik, everyone is sleeping. Sleeping is a bad habit for you guys. Anyways, F minus F is equal to ma. Now here in this F minus F, if I talk about this F minus F is nothing but your net force. I hope you understand this. And this m into a is your Newton's second law. F net is equal to ma. That is how we have written this equation. So now I can relate this acceleration as with Newton's second law of motion. This acceleration multiplied by the mass m will give me the net force acting on the particle. Remember, this F net is the net force. Ma is not force. Ma is basically whenever we have net force, that must be equal to mass into acceleration. So mass into acceleration in itself is not a force. When you multiply mass with acceleration, that will give you the net force. Now this net force can be gravitational force. This net force can be frictional force. This net force can be spring force. It can be a combination. M into A just gives me the net force. M into A is not a force. M into A gives me the net force. I hope you understand this. When I am lifting this pen, I am applying a force. Contact force or whatever you call it. That is a force, that is a real force. But m into a, if it is accelerating, m into a is not a force. M into a is mass into acceleration. Mass into acceleration gives me the net force, which may be a combination of different types of forces. Do we understand this? The difference between ma and f net. F net gives you the net force acting on the particle. That net force will be equal to mass multiplied by the acceleration of the particle. I'll give you a minute to note this down, then we will move ahead. I hope everyone understands this. Well, I hope everyone has noted this down. That was acceleration. Now, what we have studied in this particular topic is this acceleration can be thought of as consisting of two components. The first one is, let us talk about AT. AT. Now, if I have to write AT, this direction will be in the same direction as velocity, or it will be in the opposite direction of velocity. Let me just talk about the magnitude of AT, because it is easier to understand the magnitude of AT. The magnitude of this AT will be equal to rate of change of speed, which is Vt, or I can write it as d by dt of Vt vector ka magnitude. This is nothing but rate of change of speed. It is telling us the rate at which speed of the particle is changing. Now, this tangential acceleration again will come from some force. Acceleration is tangential. So I'll call that force as tangential force. Ft, F tangential. Now this F tangential, the net tangential force will give me mass multiplied by tangential acceleration. I hope everyone can relate this one with the upar wala one. In the upar wala one, I had the total net force. In the upar wala, I had the total net force. Let me color it with blue. I had the total net force. Total net force, F net, is mass into acceleration. If I only talk about the tangential component, the tangential force Ft will be equal to m into at. Do we understand this? Can I have some raised hand that we understand this? So if I multiply mass with tangential acceleration, I will get the net tangential force. Do we understand this? Can I have some raised hands that we understand this? Now this tangential force can be gravitational. This tangential force can be frictional. This tangential force can be spring, or this tangential force can be contact force, or it can be a combination of any two or any three of these. So m into at will give me the net tangential force. This tangential force is the real force, which can be a combination of friction, gravitation, normal reaction, contact, tension, whatever you can think of. So this tangential force is responsible for changing the speed of the particle, because this tangential force gives us the tangential acceleration m into at. When you multiply m into at, that will be equal to net tangential force, and this net tangential force can be a combination of any of the forces that we have studied so far. Do we understand this? Can I have some raise hand that we understand this? The relation a vector, from a vector, if you multiply a vector with m, you get the net force. If you multiply m with at, you get the net tangential force. I'll give you a minute to note this down. Well, I hope everyone has noted this down. Now, if you have noted this down, then we must now come on to the third part. We've done acceleration. We have done tangential acceleration. The next part that remains is your centripetal acceleration, or normal acceleration, or radial acceleration. Now, the centripetal acceleration can be written in the vector form as omega cross vt. We all know this. If I just simply write it in terms of scalar, it can be omega multiplied by vt. That is not the form that we normally use. The normally used forms are omega squared multiplied by r, or vt squared divided by r. We all know this. Now, if something is just changing its direction, listen to me very carefully. If somebody is just changing its direction, it may not be changing its speed, it is just changing its direction. Just changing its direction. So, whatever is changing its direction, whatever object, whatever body is changing its direction, it always needs, since the direction is changed, velocity changes. But velocity only changes in direction. If velocity only changes in direction, whatever changes direction, it must have centripetal acceleration. Must have centripetal acceleration, even though it is uniform circular motion. Speed does not change. Angular velocity does not change. There is no angular acceleration. But the direction of velocity changes. It always moves in a closed path. The direction changes, and hence there is always centripetal acceleration in the picture. Now, someone has to give you this centripetal acceleration. Take. If you got to turn, take this centripetal acceleration. That force is now known as, no prizes for guessing this, Fc. And this Fc is known as centripetal force. So now we welcome the main hero of this chapter, centripetal force. What does this centripetal force do? Now, this centripetal force can be any force that we have studied till now. It can be your tension in the string. It can be your gravitational force. It can even be your spring force. It can even be your frictional force. It can even be your normal reaction force. It can be anything. It can be a combination of these forces. This centripetal force will be giving this body the centripetal acceleration. And what would be the relation between this centripetal force and centripetal acceleration? It is very simple. The relation would be simply m multiplied by ac. If I write it in the vector form more elaborately, I can write this Fc vector as m times omega cross Vt vector. This is the best way to write it. If I just talk about the magnitude of this centripetal force, I can write it as m into AC, or I can write it as m into, oops, m into omega into Vt, or I can write it as m omega square r, or I can write it as m Vt square by r. Remember, this m into AC is not a force. This m into AC actually is the net centripetal force. This net centripetal force can be given by any of the forces. I'll give you examples. I'll give you examples for that. But first, I'll give you time to note this thing down. I hope that this is clear to everyone. Can I have some raised hand that we understand this? FC is m into AC. Great. Everyone has woken up. That is good. A minute, 2 minutes. The time starts now. Well, I hope everyone has written this. Now, this centripetal acceleration, if I just give you an example, who is providing this centripetal acceleration example? Let us take the first example. Who is providing you with this centripetal acceleration? Who is providing the centripetal acceleration? Let us take the example. Let us take the example of this. Let us say this is Earth. The center point is Earth. And this gentleman is moon, m, small m, m. Now this moon is moving around the sun, and the path is almost circular. It is almost a perfect circular path, and this is probably the only system in the universe where a particle is moving, where a satellite is moving around a planet, and the path is actually completely circular. In all these cases, in all the other cases, wherever a planet is moving around a sun, or planet or satellites are moving around planets, the motion is elliptical. I hope gravitation is going on. In the other class, you must be knowing that the path is elliptical, but this is the case of a perfectly circular motion. Moon is moving around Earth in a circular path on a curve. It must have centripetal acceleration. The question is, this centripetal acceleration would be coming from some centripetal force. Which force? Right now, here, moon moving around Earth is giving the moon the centripetal force to move around Earth. Can you give me an example? Can you tell me, not an example, the example I am giving you, can you tell me which force is giving moon the centripetal force required to move around Earth? Which force is giving it the centripetal force? Anyone? Which force is giving moon the required centripetal force so that it moves around Earth? Which force is acting at centripetal force in this case? Which force is acting as centripetal force in this case? No one has any idea? What keeps moon moving around Earth? Yes, Surendra, that is the gravitational force, and this gravitational force is attractive. Fg. This gravitational force is attractive, Fg. And now, since you have already studied the chapter on gravitation, and if the radius of this circle is r, everyone knows, sitting here in the room, that this gravitational force Fg, I'm only writing the scalar notation, will be equal to g into mass of the earth, m, capital M, mass of the moon, small m, divided by r square, which is the distance between the center of Earth and the center of Moon. Do we all understand this? Can I have some reason that we understand this? This is definitely the gravitational force between Earth and the Moon. This force is the real force. Yes, it is the real force. But this force is responsible for this particle, this moon moving around Earth. Therefore, it is giving the moon the required centripetal force. So if I just write the centripetal force like this Fc, this must be equal to your Fc, and that must be equal to m mass of the moon into Vt square divided by r. Do we all understand this? Yes or no? Can I have some raise hand that we understand this? Gravitational force is giving moon the required centripetal force, which is m multiplied by AC, and AC is simply Vt square by r, or omega square into r, or omega multiplied by Vt. We all know this gravitational force. Now we just understand that this gravitational force is giving the required centripetal force. I'll give you one more example, and in the coming discussion we will see a lot of these examples. One more example of circular motion, and let us take the example of this. This is a vertical circle. I have a string and I have a stone attached to the string, and I am moving this stone like this. You might have, I mean, you kids are very digital of the digital era, but in my era, the 1990s and 80s, I'm born in the 70s actually. 79 is my year of birth. We used to play with something known as langar. So what was that langar? It had a string, daga, and we used to tie a stone at the end of that, and then we used to play with that, move it like this, and play with that langar. We call it langar in Hindi. I don't know what is known as in other languages. I even don't know what is it called in English. Anyways, a string. This is a string of length L, and then we have a small mass M attached to this string, and we move it like this. Dung, 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 dung. So it moves like this. It has a tangential velocity Vt. At the lowest point, it will have different velocities at different points. We will be seeing this in detail in the next classes. Now the question arises. This is moving in a circular path. Yes, 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 yes. Someone must give it centripetal force. The question is, who is that gentleman? Who is that gentleman who is giving this body the required centripetal force to move in a circular path? If I draw the free body diagram of this gentleman, mg is downwards, tension T is upwards, and now you know which force, or what is the force that is giving it the required centripetal force right now at this point in time. Can anyone tell me that? Centripetal force is directed towards the center. Remember, it is F into M into AC. It is the net force. If your thread is weak, you will just break and you will not be able to move it. So your thread must be strong enough to hold that mass. Tension, yes, students on the class, tension is there, but remember, it's the net force. Apart from tension, there is also one more force acting on this particle. Don't forget that force. Net force towards the center is equal to centripetal force. Net force. Don't, you have pointed out the right one, tension, but there's also one more which you have forgotten. The answer is obviously tension, but we have to be theoretically also correct. The net force is FC, and the net force here is, oops, wrong color. I don't use wrong colors. The net force here is T minus mg. Do we all understand this? It is same as what we had done. Net force, it should be equal to the centripetal force. Do we understand this? Upwards T, towards the center T, outwards mg. Net force is T minus mg. Do we all understand this? Can I have some raise hand? T up, mg down, T minus mg. Oops, wrong color again. T minus mg becomes my m into AC. That becomes m into Vt square by L. Do we all understand this? Look at here, Fc, it is upwards toward the center. T is upwards, mg is downward. We have to find the net force. This is exactly similar to what we had done here. Go back to the past and see. Yes, see here, see here, see here, see here. The green one. F was aage, small f was piche, forward, backward. We found out the net force F minus F, that was equal to m into A. Same concept is here. Net force towards the center. Net force towards the center. I hope I am making myself very clear. Can I have some raised hands? That we all understand this. It's the same concept, same thinking that we have studied so far back. Just applying it now on circular motion, and this is how it looks like now. This is how it looks like now at this point in time. I will end today's class here on this note, and I'll keep this screen on for you so that you can note this down. If you have any doubts, you can ask me, note this down, and you can leave your class. I'll meet you in the next class. I hope you have enjoyed today's lecture. I'll meet you in the next lecture, and we'll continue our discussion on this centripetal and tangential forces. That will be coming up in the next class. I hope you have enjoyed today's class. Take care. Have a nice day. Stay home. Stay vaccinated. Get yourself vaccinated. Today I'm going and getting my mom vaccinated. The reservation is done for 1 p.m. nearby center. I'll go and I'll get her precautionary dose. She is due for the dose, and I hope whosoever in your family is due for the dose, get them the vaccine dose. You all also get the vaccine dose. That's the only way we can be safe. Take care. Have a nice day. Tata.